And welcome to Chapter 11, where we're going to be talking about solutions. This will largely be focused on things dissolved in liquids, but not exclusively so. To start off, I'm going to be going over these things fairly quickly to a large degree, because I expect you'll have heard a lot of it before. But I don't know that, so I'm going to at least cover it, and then link you to other videos where I have covered it in more detail. Now let's start with what a solution is. A solution is a homogeneous mixture of two or more substances. So homogeneous means that it is uniform throughout. You cannot distinguish one region of the solution from another region of the solution. The other thing to recall is that for the solute, the thing present in lesser quantity, they all experience the same sort of environment. That'll be important when we come to colloids toward the end of the chapter. So because the solute particles, the thing that's present in lesser quantity, are present in lesser quantity, they are completely surrounded by particles of the solvent. So they're all experiencing the same sort of environment, whatever environment that is. Whereas the solvent, because it's present in so much greater quantity, they don't always experience the same sort of environment. You know, some particles of the solvent might not encounter for a long period of time any particles of solute. But the particles of solute always encounter the same sort of environment, being completely surrounded, that is, by particles of solvent. This definition can kind of break down if you have two perfectly soluble sorts of things, such as water and alcohol. You increase the quantity, you start off with pure water, you drop alcohol in there. As you increase the quantity of alcohol, eventually you're going to come to a part where, they're just going to be present in equal amounts. You can't really call either one the solute or the solvent. And at that point, it's kind of hard to say if each particle is experiencing a similar sort of environment. And you should sort of focus more on the fact that regardless of the sort of small-scale fluctuations, whether this particle of alcohol is surrounded by more particles of water or more particles of alcohol, the solution itself over time is uniform. And that definitely isn't true for colloids. And finally, for this slide, dissolution is the act of dissolving. So we'll go into that in a little bit more detail. Okay, and first I want to go through just a few examples of different kinds of solutions. You can get a very wide variety of solutions. They're not all, just solids dissolved in liquids or liquids dissolved in liquids. Okay, for example, you can get gases dissolved in gases. The only thing a gas can dissolve is another gas. Solids and liquids are capable of dissolving solids and liquids because they have the structure capable of holding those other things. Gases, they don't have any sort of structure. The particles are separated by enormous distances. So it's not so much that they're dissolving in one another as that they are free to mix in one another, and there's nothing to stop them. So just the air you breathe is an example of a solution, a gas solution. It's got mostly nitrogen, then some oxygen, and then very small quantities of carbon dioxide and other gases. You can also dissolve gases in liquids. Okay? So carbonation is an example of a gas dissolved in liquid. That's gaseous carbon dioxide, CO2, dissolved in water. If you dissolve other things in there, then you'll get soda. And the reason it's called soda, by the way, is because it used to have sodium carbonate in there. Lots of things, anything made with a sodium salt often has soda in the name. So soda glass was another thing made with a sodium salt. All right, you can also get liquids dissolved in liquids. So liquor, anything, alcohol dissolved in water, is one example of a liquid solution. You can also get solids dissolved in liquids. So hard water is a solution of calcium carbonate dissolved in water. Calcium carbonate is also known as limestone, and it's not very soluble. It's very insoluble, and it does not want to be dissolved in your water, and it will take any chance it can to come out. So that's one of the reasons why hard water is bad, is because it will coat the inside of your pipes with what's known as lime scale, and just basically slowly choke off your water pressure. It also causes your soap not to work as well, because the calcium ions will react with the ions of your soap and just pull the soap out of solution, so it no longer does soapy stuff. You can also get gases dissolved in solids. Remember, you've seen now that even solids have a lot of empty space in between the particles, and you can get gases moving in between the particles of a solid substance. And hydrogen, because it's so very small, is particularly good at that. But you can get other things dissolved in these solids of whatever you're looking at. You can also get liquids dissolved in solids. Those are not quite as common, just because the liquids tend to take up a little bit more space. But mercury likes to do that with some other metals, and it forms what's known as an amalgam. An amalgam is a special name for an alloy of mercury with some other metal. So mercury will pretty much instantly dissolve into gold or silver. It's very hard to separate them once that happens, and they become toxic, and so it can ruin gold or silver. All right, and finally, a solid-solid solution is a more typical alloy. So carbon dissolved in iron will make steel. You get zinc dissolved in copper. That will make brass. If you dissolve tin into copper, that's what makes bronze. And carefully selecting what you want to dissolve into what other substances will greatly alter the composition of your alloy, because of the way the different sized atoms can fit into one another's structure. So when carbon dissolves in steel, it fits very nicely in the gaps inside the body-centered cubic structure of iron. Similarly, zinc fits very nicely into copper. Copper fits nicely into tin, and that's why it makes a very, very strong bronze. And those are just some examples of solutions. And remember, that solution, just uniform properties throughout, and that's what makes it a solution. And all of these things, gases, liquids, solids, mixing together, you'll get a uniform property throughout the solution, regardless of the physical phases of the materials involved. And now I would like to talk about solvation, or dissolution. This is the actual physical process that happens when you mix two things together. We are talking fairly specifically about dissolving into a liquid now. It kind of happens the same way when you dissolve into a solid sometimes. But the processes that take place, you have to actually make them happen if you're talking about dissolving a solid into a solid. Just because, they're both solids, and you have to beat the crap out of them with a hammer to make them actually mix. But as for dissolving something into a liquid, it's a little bit easier, just because the particles of a liquid are in constant motion, and it doesn't really have that solid structure that's locked into place. So it's a fairly simple three-step process. If you're dissolving A and B together, if you have particles of A and particles of B, the first thing you have to do is you separate them, so that you have to, because remember, solids and liquids, the particles are always touching. We're not talking about gases here. But for a solid and liquid, you have to separate them enough. You have to open up space in between the particles. So that's the first thing to do. And then you can mix them together by putting particles of A into the spaces in between B and B in the spaces in between A. And remember that we can look at it this way because we're talking about state functions, okay? Remember Hess's law and that wonderful thing. The processes don't really take place in a nice stepwise fashion, but we can pretend that they do, so long as we're only talking about step functions or state functions, and that works very, very well for something like this. When you mix A and B together, you don't get this discrete, open up the formation, now mingle. No, it sort of happens piecemeal, that they encounter one another and they explore the space and they sort of mingle and separate at the same time. But this is a good way of thinking about it. You can think about, the step where A separates. You can think, and separate thing, another step, a different step where B separates, and then a third step where the two different substances come together. And that lets you think about the way this process happens and the energy and things like that are changing as it happens. And whether or not this will actually happen, that depends upon two factors, enthalpy and entropy. Enthalpy, that's delta H, okay? Hopefully you recall that from discussions of thermodynamics. For a process that takes place at constant pressure, delta H is just equal to heat. It's just the energy, or the particles at lower energy when they're mixed together. You can think of enthalpy as being a measure of the attraction of the particles for one another. Are the particles more attracted to one another than they are to themselves? Okay, so a adhesion sort of thing. The other factor to consider is entropy. We have not covered this before, but you may have heard about it. Entropy is often called a measure of disorder. That's not exactly true, but that is a good enough proxy. And mixing almost always involves an increase in entropy, just because there are more ways to have things all jumbled together than there are to have them all tidy and separate. So entropy almost always favors mixing. So whether or not two things mix usually comes down to enthalpy. And that's just a matter of how similar, how attracted the particles are to one another. So, for example, water is very good at dissolving polar compounds and ionic compounds just because they're very similar, and it does not require a great disruption of the structure of either one to get them to mix together. They're very happy together. Whereas oil and water don't mix, because in order to get the particles of oil to dissolve in with the water, it causes a great deal of stress on those particles of the oil, because the oil is non-polar. It doesn't have that separation of charges the way water does. So you would have to stress the heck out of every particle of the oil in order to get it to move in among the particles of water. So that prefers not to happen. Even though entropy would say it would, enthalpy says, no, God, no, we hate each other, we're not going to mix. And we've gone a little over the 15-minute mark, I think. So we will come back and talk more about solutions in the 8th lecture.